Hi, this is Professor Fernandez, and in this video, we are going to work out an example of calculating Maclaurin polynomials. This comes from the notes for lesson 13 are available on this website where you'll find these other resources. First thing I want to do is to remind you what a really Maclaurin polynomial for this particular video is. So I'm going to zoom in here on the bottom. This is the definition of a Maclaurin polynomial from the notes from lesson 13. So it says, suppose f of x has n derivatives at x equals 0. We're thinking here of n as a whole number, quote unquote, that's positive, like 7 or 35. The definition says, then the nth degree polynomial, m sub n of x equals this, is the nth Maclaurin polynomial of f. Okay, so a couple of things to say about this. First of all, there is an assumption that f has enough derivatives for the nth degree Maclaurin polynomial to make sense. So this means that the function needs to be differentiable enough times. We'll get back to that when we start working out the examples. Second thing to say is that the Maclaurin polynomial is a polynomial, right? So polynomials have the form sums of products of coefficients a sub n with power functions x to the something. So this is a example of a general polynomial. What's special about the Maclaurin polynomial is that the coefficients have a very specific form. So the nth coefficient in a Maclaurin polynomial is the nth derivative of the function evaluated at 0 divided by n factorial. So you see that over here. This is the a sub n term. If you're wondering why that is so specific and where that came from, I'll invite you to take a look at the notes for lesson 13, where I discuss basically how that comes about. And long story short, the answer is if you're trying to approximate a function by some other by a polynomial, really, then one of the ways you can do that is to try a linear approximation. You might try, I don't know, a quadratic approximation. You might try a cubic approximation. And as you see me drawing these curves, I'm trying to draw them to get your intuition to think, oh, if I add more and more, if I increase the degree of the polynomial, the approximation gets better. But certainly, like the actual coefficients, right, in the polynomial that you're using to approximate the function, they have to have kind of specific numbers, if you will, to get the approximation to be fairly accurate. These turn out to be those numbers if you want to match the y value at 0, x equals 0, the derivative at x equals 0, the second derivative, so on and so forth. Okay, so that's a quick tour of Maclaurin polynomials, what they are, what makes them special as particular types of polynomials, and a little bit of intuition as to why they have this particular these coefficients. Again, I'll send you to lesson notes for lesson 13 for all the details. So let's go back then to the example. And here we want to calculate the nth Maclaurin polynomial for the functions below. So first one we'll start off, is f of x equals e to the x. Remember, the only requirement to calculate these Maclaurin polynomials is that the function is differentiable up to n times. So, and we're actually going to need to calculate those derivatives to find the coefficients, and I'll show you why in a minute. So here's the function, e to the x. So I'm going to just start calculating derivatives. You might be able to see why I started off with this function, because the derivative of e to the x is e to the x. So it's really easy to go off and calculate the derivatives all the way up to the nth derivative, because the answers are always the same. It's always e to the x. So the only assumption is met. The function that we're looking at is in fact differentiable n times. Okay, now the Maclaurin polynomial says take all those functions that you just got and substitute in x equals 0. E to the 0 is 1. F prime of 0 is also e to the 0. That's also 1. And so on and so forth. And then the nth derivative at 0 is e to the 0 again. That's 1. Okay, so these are going to are what you're going to use to build the coefficients, the a sub n's, for the Maclaurin polynomial. Remember, those are nth derivative evaluated at 0 divided by n factorial. So at this point, really, one of the intermediate goals of writing down an nth degree Maclaurin polynomial, or Taylor polynomial for that matter, we'll talk about that in the next video, is to find a pattern for the nth derivative evaluated at x equals 0. It turns out, for this particular example, because we're talking about e to the x, that the answer is always 1. So the numerator here is always 1. So a sub n is always 1 over n factorial. So that makes it really easy to write down the nth degree Maclaurin polynomial, right? Remember that was f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus all the way up to nth derivative at 0 over n factorial x to the n. I now have all of these coefficients, right? I know what they are. F of 0 was 1, f prime of 0 was also 1, f double prime of 0 was also 1, right? All the coefficients, remember, evaluated at 0, all the derivatives evaluated at 0 of the function were 1, plus dot dot dot, including, in general, the nth derivative evaluated at 0. That is 1. So 1 over n factorial x to the n. So if I had to simplify this a little bit, I would just get rid of a lot of the 1's in the numerator and write it this way, right? And that is our nth degree Maclaurin polynomial. You might see both the definition down here and when you express your answer, you might see them in sigma notation. So let's do that. First of all, the definition in sigma notation, right? So the nth Maclaurin polynomial in sigma notation, we're adding, and what are we adding? Notice that, I'll zoom in here, the order of the derivative, in this case first derivative, matches the power of the function, x to the first. Second derivative, x squared. Nth derivative, x to the n. Also notice that the denominator of the factorial matches the power of the function. 2 factorial, x squared, n factorial, x to the n. So that makes it pretty easy for us to write down the sigma form because it's going to be nth derivative. And actually here I'll use a different letter. I'll use k. I'll show you why in a minute. Kth derivative at 0, x to the k over k factorial, right? The order of the derivative matches the power of x. The factorial we're taking matches the power of x. And then where does k start? Well, we start with f of 0, right? That's k equals 0. There's no x to the anything. It's x to the 0. And where do we end? We end with x to the n. So there's an n over here. And that explains why I chose k as the index here, right? I didn't want to choose little n because then I would have like n equals 0 to n. And that's kind of a no-no when you write out sigma notation, right? The ending value of the sum should not be the same variable that you're using to track the terms themselves. So that explains why I chose a k. Okay, so this is a closed form, a sigma notation expression of the Maclaurin polynomial. You can see what I was saying a few minutes earlier in the video, that if you know this quantity, and really knowing this quantity is about knowing the kth derivative at 0. If you can spot that pattern, then all you have to do is substitute it in. So if we did this version of the solution here, then x to the k remains, k factorial remains. And for this problem, if I scroll up, remember we had found that the nth derivative at 0 is 1. Doesn't matter if it's n or k or any other variable, right? So this is 1. So I put that in here. So in sigma notation, this would be sum from k equals 0 to n, x to the k over k factorial. Notice that that's exactly what we got by writing it out each, term by term over here. So all that confirms, one confirms the other. Okay, so let's do this again now for a different function, and we'll speed it up a little bit because now we know all the ins and outs of what's going on. So the different function here is sine x. So same procedure. So we'll start off with the function, and then we'll start calculating derivatives, right? So f prime of x is derivative of sine, cosine. F double prime of x, derivative of cosine, negative sine. And then we can keep going here. It's not as easy as the e to the x example we just did, but there are some patterns, right? So once we get to the fourth derivative here, the derivative of cosine is negative sine, multiplies times that negative sine, SIGN, to give you back sine x. So we started with f of x. By the time we get to the fourth derivative, we're back to the function. So you can kind of see how this is going to go if we were to keep differentiating. We've spotted the pattern now, and we could work to quantify it, but we won't need to. Okay, next we will substitute in x equals 0. Remember that sine of 0 is 0, and that cosine of 0 is 1. And then we kind of keep going here, again looking for some patterns. Minus sine of 0, that's 0. Third derivative, minus cosine of 0, that's minus 1. And then fourth derivative, evaluated at 0, back to the original value of the function. Okay, now see, we didn't have to quantify the pattern in the derivatives, like nth derivative of x, of f of x. We can instead try to quantify what we really need for the Maclaurin polynomial, which is the nth derivative evaluated at 0. So that's all of these numbers. And here, there's a pretty clear pattern. So 0, positive 1, 0, negative 1, 0, probably the next one is positive 1. So we can start writing out then our nth degree Maclaurin polynomial, f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus, in this case, negative 1, f triple prime of 0 over 3 factorial x cubed, and then plus f fourth derivative evaluated at 0 over 4 factorial x to the fourth, and so on, right? There's going to be an x to the n term here. We know it's going to involve an n factorial. We don't quite yet have a way to express what's going to be here. We can see the pattern here. We just haven't quantified it to know enough as to what to write here. But that's okay, because let's simplify what we've just written. And by doing that, you'll see in a minute that we'll spot another pattern. Okay, so this goes away, the 0 here, so we just have 1 times x, that's x. This term goes away, so the next one is minus x cubed over 3 factorial. This term goes away, and then if you can see what the next non-zero term would have been here, right? It would have been fifth derivative evaluated at 0. Go back over here. Fifth derivative of x here, derivative of sine, that's cosine x. Evaluated at 0, cosine 0, that's 1. So that's the coefficient of f, the fifth derivative evaluated at 0. That would have then gone over here. It'd be plus 1 over 5 factorial x to the fifth. Remember, this 5 matches this 5 matches that 5. So we have a plus x to the fifth over 5 factorial. This is enough to give us information about what the pattern is, right? First of all, a couple of things to note. All of these powers of x are odd. And all of the denominators, remembering that 1 factorial equals 1, all of the denominators are the factorial of the power of x. And last pattern here, this is plus, this is minus. This is plus, so alternating. Great, so if we wanted to then write this out, I'll just put this, and again, the last term is going to depend, right? If n is even, then that term isn't there. If n is odd, then there is a term there, and there's an alternation in sign. So what we're going to do then is to write out the sigma notation version of this to put in the patterns that we just found a little easier. And I should say, at this point you can probably stop here. Most of us instructors will be like, great, you found the Maclaurin polynomial, you know that it's alternating, you got all the right coefficients, that you've done a lot. Okay, so how do we write an odd number? So first of all, x to the 2k plus 1. 2k plus 1 is a way to express an odd number. Again, we're thinking of k here as a whole number, quote unquote. Because, for example, 2 times 1 plus 1 is 3 odd. 2 times 2 plus 1 is 5 odd. 2 times 3 plus 1 is 7 odd. So you can see I'm generating all the odd numbers as I just substitute in successive k values into 2k plus 1. So 2k plus 1 is one way to express an odd number as k ranges from 0 to infinity, gives you all the odd numbers. And then we divide by that same thing factorial. Okay, and then we're going to add as k goes from 0 to something. Okay. And at this point, we're going to put then minus 1 to we have to figure out the power. So let's think about this. K is starting at 0. And when I put k equals 0 in here, and in here, I just get x to the first over 1 factorial. Hey, that's this term. And that term is positive. So if I go back and look at my sum, oops, there we go. If I put, for example, a k here, that's going to work out, because minus 1 to the 0, that's positive 1. And then the next term, k equals 1, would give me a negative, and that's actually the next term in the sum. So we've double checked that that works out. And then here's where you could just put as the upper limit of the sum, you could just put here n. Right? In other words, you don't have to exactly figure out a way to get the last term of the sum to be exactly x to the n. This sum here is going to start off x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot 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 plus, and then what is the nth, what is the last term in this sum? Well, it's all of this with an n. So minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, and that is a really, really good way to express the Maclaurin polynomial for sine x. Okay, and then again, the closed form sigma notation version to declutter it a little bit so you can kind of see it a little easier. And then maybe also move it over so we can appreciate it over here. There we go. So this on the left-hand side over, I should write the actual notation we're using, mn of x. So on this left-hand side, oops, that's a little too far. On this left-hand side over here, that is the sigma notation closed form expression of the Maclaurin polynomial for f of x equals sine x. And then on the right-hand side here is written out, written out term by term. Last thing I'll mention here, sometimes you find some curious, what would I call them? Consistencies or just curiosities between the Maclaurin series and the function it came from. The function sine x is an odd function. Remember, this means that when I put in negative x, it's equal to sine of negative x. We have this property that that's equal to minus sine x, so I get minus f of x. If f of negative x equals negative f of x, then we call the function, in this case sine, odd. Isn't it odd, if you will, that the Maclaurin series, Maclaurin polynomial of sine x contains only odd numbers, right? So again, a curiosity, right? The naming of odd and even, as far as I know, had nothing to do with powers in the Maclaurin polynomial for the function, but it just turns out to be related. Anyway, if you do know that there is, in fact, some relationship between the two, or that historically the name, of odd function followed odd numbered, odd powers of x in a Maclaurin polynomial, please drop it in the comments, and I'd love to hear about it. Okay, thank you. That's all for this video. Thanks for watching.